Awesome. Thank you all for coming. So I'm Mark Hamilton. I'm a software engineer on Microsoft's Applied AI team, and I run Microsoft Machine Learning for Apache Spark, which is Microsoft's collection of open source contributions to the Apache Spark ecosystem that aim to bring it into places that it hasn't ventured before. So today's talk is going to be about one of our sub-projects, Spark Serving, which is a project that aims to unify Spark's existing batch and streaming APIs with a new API for RESTful serving that feels and looks the same, but gets you great performance and is very easy. So the overall structure of this talk is we'll go over kind of what Spark Serving is, the basic 101s, how to use it, what the anatomy of a query looks like and its performance, and then we'll dive a little bit deeper. We'll get into the architectural details, how we handle things like fault tolerance, shuffles, and replying from within existing computations. And then we'll talk a little bit about a related project, namely HTTP on Spark, which is a fundamental integration between the entire HTTP protocol and Spark that kind of handles the dual side, not just Spark as a web server, but Spark as a web client. And finally, we'll cover how to set this up in a variety of different ecosystems. So Kubernetes and Azure Machine Learning are the two that we'll focus on. So a brief motivation for this project is that you really want to be able to create web services with the computations you do in Spark, because creating a web service is the best way to share your code with others from across the organization to down the hall, in different languages. You don't need to actually share the bits or figure out how to do bindings. You just share a web endpoint and anyone can call it. And so a lot of the systems that exist today for deploying models on Spark rely on either exporting Spark pipelines or using the existing high latency batch APIs. And both of these have problems in their own right. Exporting requires you to do double duty on the dev front. You not only have to code the model, but you have to code it in whatever export language you have. And the high latency batch API, well, it's high latency, so you're not going to get great performance. And more generally, Spark's philosophy throughout these years have been to unify everything within a single API. And you can kind of see that philosophy throughout where you look at the data sources API, where you have a million different data sources under the sun, all with the same spark.read.datasourcex. And you have a lot of different kinds of computations that you can do in Spark. Like you have the whole SQL universe, you have the whole MapReduce kind of universe. So it really aims to be something that is very general. And what you hear a lot about is that Spark has this axis of generality, which is either batch or streaming. So when you write your batch computations, like spark.read.parquet, and you do some selects, some maps, some UDFs, you don't need to change anything if you want to turn this into a streaming computation. You just change spark.read to spark.readStream, and maybe point it at a different source like Kafka, give it some parameters. And so what we'd really like to accomplish is to have a very similar API, something that looks and feels just like the top two, but instead creates a web service. And so what this project aims to do is just that. That's Apache Spark Serving. And the idea is that we want to provide an API to be able to take your existing Spark cluster and turn it into a distributed web service provider. And so the code is over here on, I guess, your right. And so the basic look is that instead of reading from Kafka or something like that, you read stream from a server. And this will boot up and manage a server on each one of your worker nodes. And then you can work and manipulate it just like you do a regular data frame. You can apply anything in the Spark ecosystem that works with Spark streaming. And then the key abstraction here is that a server is kind of like a stream where the source and the sink are the same web request. And so that's where this paired sync comes from. And what's nice about this is that we can get sub-millisecond latencies. It's fully distributed using your existing Spark cluster. It spins up really fast, about at the same time as it takes to spin up a streaming query, which is like less than a second. You get the same API as batch and streaming. And we've worked to provide bindings for this in Scala, Python, and R. And Java comes for free from Scala. And it's fully open source, so you can go ahead and check out the source code, contribute, and give us feedback. So now we can take a look at a particular example. I showed this off in the keynote, but we had to blow through it because we had like 3 minutes in order to do that demo. So how many of you guys saw the keynote yesterday? OK, so a bunch. So I won't spend too much time on this. But what I do want to focus on, I'll rerun some of these queries here, is the serving part. So as a little bit of background while this stuff runs, what we've done yesterday is that we used Bing image search to pull a large data frame of images of currency notes and then train a deep classifier to predict these currency notes. I guess we don't need to plot the confusion matrix. This will save us some time. And we train a classifier in order to predict these different kinds of currency notes. And the idea is that we want to be able to create an automated system for the visually impaired that can take an image of a currency note and tell you what you're actually looking at, because there's no real way to tell the difference between banknotes or something like this from their look and feel alone. So it's almost done. And so we'll take this time to take a look at what it actually looks like. So here, I'll zoom in a little bit, is the basic structure of the computation. We say spark.readstream.continuous server. This is the variant we have for continuous processing. We give it an address. We want to pull from localhost 8089, and our path is predict. We then can load this computation, and you now have a data frame that you can do whatever you want with. The structure of this data frame is actually the full structure of the HTTP request, and so we'll parse that out into a binary. So people will send up images of dollar bills to our web service. And then we can use the standard SparkSQL operations. In this case, I can rename the column bytes to the column image to fit with our model. And then I can then use our model that we've trained to just transform the serving data frame. And so this is just a regular SparkML model. Any of the existing SparkML models will work with this if they work with structured streaming. And finally, once we have our predicted labels that come out of our model, we can go ahead and package these up into a reply and write them back to the server. And you'll see that there's a reply to command that we've added, and this basically tells you that you want to reply to the sink that you made up here, or the source that you made up here, because sinks don't really have any knowledge about which sources they came from. So we can kick this off now. It's probably ready to go. And in just a few seconds, we see that our serving data frame has an ID that's used for routing and an image that's a binary, and it's already kind of up and ready to go using the nodes of our Spark cluster as its backend. And so that's like how quick and easy it is to just take your existing model and turn it into a web service on your existing Spark nodes. And so we can take a look at in greater detail about what's actually going on in this computation. That kind of small little bit of Fluent code is doing a lot, and I want to actually be able to go through and show you what is going on. So the first step is that we just get into the spark.readstream menu. This kind of gives you access to all the different streaming data sources. And we've added this new data source, the server data source. And it takes a few parameters, namely the host, the port, and the API path. And this is what you will actually call on each one of your workers in order to contact this server. We give it a name so that we can associate it later with the sink. And then we load it. And at this point, after this .load, you now have a regular data frame. It's a streaming data frame. It works just like any other streaming data frame. We've added utility functions to parse the incoming request body to whatever schema you have. If you give it binary, it'll just pull out the bytes of the request payload. If you give it JSON, it will do the JSON unpacking and give you a nice schema. We can then transform it with whatever SparkML model that you have. And this .ml transform is also something that we've added. It just makes it a little bit cleaner. You don't have to add an extra var in there. And we can then pack it back together to be the Spark web response type. And so the reason why we have these types for web requests and web responses is that we could be fully general. We can handle the full HTTP protocol and kind of layer these APIs on top to make it a little bit more human usable if you want to do a standard thing like accept a payload and return a payload. Finally, we write the stream out to a similar paired sink, and we tell it which source we're writing from, and we start it. And what's nice is that a lot of stuff you get for free. because it's hooked into Spark streaming, you get the fault tolerance, you get that whole nice async API to see your query progress, to add callbacks to different things that happen in your query, to automatically reboot your queries, to do the checkpointing, these kinds of things. And so when we actually look at the performance, we find that we get kind of the best of both worlds. We get this sub-millisecond latency response time of these frameworks that actually require exporting to a single-threaded thing like MLeap, but we also get the breadth of models that no longer do you need to rewrite all of your Spark code in order to get it into a low latency response. You can just use what you have already. And so most of the frameworks, as I said before, kind of fall into one or two of these camps. So a few of the projects in the past, like PMML, Onyx, and MLeap, you'd require writing exporters, and they write exporters on the level of SparkML transformations. So if you have anything else but a standard SparkML pipeline, you're out of luck, or you have to kind of re-implement that logic yourself. And other methods like Clipper and Azure Machine Learning, at least in its default case, they leverage Spark's batch API, which incurs like around a 500+ millisecond overhead. So that's half a second of time to just create a data frame and evaluate it. And that's in local mode. That's not necessarily in the distributed mode, so there's no communication. And that really becomes untenable if you want something that's really low latency and high throughput. And so now that we've kind of seen what Spark Serving is, we can take a look at what actually is going on under the hood. And so what we do is that on each worker node of the cluster, we spin up one server that's shared between each of the partitions. And ideally, because you'd have a lot of worker nodes, you'd want to stick a load balancer on top of those services in order to tie them together and give users a unified endpoint that gets balanced across the different cluster. And so that's kind of the rough structure of Spark Serving, and now we can kind of go in and zoom in on one of these Spark workers and actually trace the path of what goes on. So we can, I think a good example of doing this is to see kind of how fault tolerance works, because you see not only the main path of code, but you also see the path if something goes wrong. So on each one of these workers, you have a single server, and we do this for efficiency, and we also do this so that it fans out across the partitions a little bit better. And every time it gets a request, it stores it in a linked blocking queue. And this is an efficient Java parallel data structure that allows you to kind of enqueue things, and then as soon as they're enqueued, pull them off so that you don't incur much latency. And so each one of these partitions is hooked up to this linked blocking queue and just waiting to pull data from it. And as soon as they pull data from it, they also add it to a history store. And this is how we can get fault tolerance, is that we keep track of all the requests that we've received, which partition took them, which epoch of the streaming computation they were in, and we store them in a nice list so that we can refer back to them later if we need to. And so at this point, we have a giant meteor that comes and destroys our second partition, and it's in flames and everything, and we have to boot up another one. You know, that linked blocking queue is this efficient parallel mutable data structure. It doesn't hold history. We can't get those requests back, and so this is when we talk to the history store. So we can use Spark's task context to figure out, hey, we're in a retry. We need to change the way we get our requests. And we can pull these from the history store. And so this way, you have the same kind of fault tolerance guarantees that you have with a lot of other data sources. I mean, granted, the whole worker can go down and you'll lose your requests, but that's really it's an impossible challenge to solve, and that those are networking requests, and you can't just get those back. So this is about as good as a fault tolerance as that we think we can get. And so finally, when the requests are over, we create a new request queue for the second epoch. And so this is how we integrate with Spark's kind of mini batching framework. And then we have these kind of epochs, and each one of them creates its own queue, and the rest are cleaned up by the garbage collector. And so another thing that is nice that we've added with our latest release of ML Spark is that, a lot of times your computation, your web server isn't just something that takes in data in a single source and returns it in a single sink. Like often you want to fail fast if, say, someone gives you improperly formatted data or something like this. So we've added a series of UDFs that will help actually replying to web requests from inside of your SparkML pipelines. So in this particular case, we'll create a column, and it's basically an if statement that says if some condition holds true, we can send a reply back to our API. Otherwise, we'll just do nothing. And then we can filter out all the things that we replied to. So this is kind of a way in SQL that we can construct logic that will respond to requests and filter out all the requests that we've already responded to. So this is how, in particular, we implement kind of JSON parsing. That not only do we have JSON parsing that if you've ever used Spark's JSON parser, if you give it crazy data, it just spits out a null. And a lot of times you don't just want to pass a null through your pipeline. You want to tell the user, like, hey, format your data correctly before talking to me. And so we kind of implement it like this, where we have a when clause that says if we get a null, if we can't parse it, then we'll talk to the user and send them back an error. Otherwise, keep on going. And finally, one of the last kind of architectural details, this is going to be released very shortly, is serving shuffles. So one of the key things that we'd like to do is that, Spark streaming, it's not just for maps, it's for all sorts of crazy computations. It's for aggregations, it's for, entire SQL queries. And so we'd like to really be able to support that kind of things, namely support the shuffle. So if you do some stuff with your data and your answer ends up on a different machine, how do we get that back to your request? Because we fundamentally cannot move the networking request. That is something I've done a lot of Googling, you cannot do. So what we effectively do is that we have our basic flow over here where when a request comes in, it gets routed to one of the web services based on a load balancer. Then the partitions pull it and start processing the data through the computation. And also we have a serving monitor on the driver node that just lets you keep track of these things and handles any additional metadata that you might want. But at response time, the idea is that it will go through a routing service. And this routing service will take a look at your IDs that are flowing alongside your data frame as one of the columns, and it will say, hey, is this held by this worker, or is this held by some other worker out in the cluster? And so using this, we can effectively either use regular function dispatch to just reply to the web request, or we can shoot that answer over via HTTP to the appropriate worker and have it respond to the web request. And I think some future work that if any of you have any ideas on would be to actually hook into Spark's underlying shuffle service to make a really efficient shuffle to do this instead of relying on our own HTTP protocol to do this. So that we can actually stream data through as opposed to HTTP where it's more of a single piece of data goes per web request. And so that kind of covers a lot of the meat and potatoes about what Spark Serving is based on. And we're now can, I guess, talk about a few of the related projects, namely HTTP on Apache Spark. And so what this project aims to do is provide a full integration between the entire HTTP protocol and SparkSQL. We create SparkSQL objects for each individual we create this kind of large nested SparkSQL object that encapsulates every single field of your HTTP request, your headers, your body, your content types, all the nitty-gritty things in the HTTP protocol. And what this lets you do is kind of have a single kind of data structure that works across the different languages. You can manipulate this with PySpark, you can manipulate this with Scala Spark, or you can manipulate this with Spark.jl or whatever you choose to use in that particular piece of code. And we, as the writers of the code in Scala, still know how to handle it because of this kind of intermediate SparkSQL layer. And so what this project aims to do is kind of do the opposite for the dual problem of creating Spark as a web server. and really tries to make Spark as a really efficient web client so that it can talk to different web servers, kind of completing the full networking stack on Spark. And over on the right, you'll see some example usage. Maybe this will be a good time for laser pointing here. We can create an HTTP transformer. This is a SparkML object that will take in HTTP request objects and return HTTP response objects. But we've made a simple version that kind of abstracts away those things. And you can pass it parsers, so a JSON input parser and a JSON output parser. And so what this will do is we'll take your Spark data, turn it into a JSON payload, contact the request, and then pull the data back out and parse it back out into its appropriate schema and return it to you in the schema that you expect for your web service. And so you can use this to kind of talk to any kind of web service that you have on Spark or off Spark. And what we really wanted to do is provide a fairly general way to just do Spark plus X, where a lot of times you'll see talks that are like Spark plus LightGBM or Spark plus TensorFlow or Spark plus this or that or the other thing. And a lot of times they rely on difficult code. You know, we've done a lot of these where you have to use Swig, you have to use tools to take business logic and move it into the JVM and move it onto the workers. But with this, you kind of just use the HTTP protocol that the whole world has standardized on, as opposed to some other kind of protocol. And so the way that this is architected is kind of very similar in that you have on each one of your Spark workers, each partition gets a web client, and it can talk to your web service using these SQL types. And so, you know, when we first dreamt up this, we were thinking of talking to cloud services. But we quickly realized that, you know, that's not the only kind of service out there. We can put services directly on the worker nodes of the cluster to have something that's much closer to a low latency, real-time microservice architecture. And so this is really the kind of vision that we hope to accomplish with these kinds of projects, is that we want to be able to complete Spark's networking stack. We want it as to be able to contact many different kinds of small web services that may live on or off the Spark cluster. And we want to be able to take those pipelines of web services and turn them into a web service using Spark Serving so that you can kind of compose and build upon your web services. And so the idea is that we've really standardized on this SparkML language for doing this. So that same language that lets you swap out your logistic regression with some complicated thing when you're ready and not have to change any of your code. We hope to provide a similar abstraction for this for all sorts of different kinds of web services. So you can pop one in and pop one out and not really change any of your code. And so now we can move on to how to actually get these up and running in production. And so some of the work that we've done mainly by Deliso Banda, he worked as part of the Microsoft AI Development Acceleration Program along with a team of 4 others. And what they've done is they've created an Azure Kubernetes Helm chart that really exposes a lot of these different kinds of functionalities out to the user. And if you haven't heard of the Helm chart, what it is Helm is more or less the package manager for Kubernetes. That's what it bills itself as. And in the same way that when you log on to your Ubuntu machine or your Red Hat machine, they'll be talking next, you can say like apt-get install and whatever it is you possibly want, and it's a single line, and boom, it pops it up. This is kind of the same for distributed architecture. So you can say, if you have a Kubernetes cluster, the idea is that you say Helm install MySQL, and boom, you get a whole MySQL instantiation on your cluster. Or Helm install Spark, and boom, you get a whole Spark cluster on your Kubernetes cluster. And so it really aims to do this and also provide a way to compose these packages in the same way that pip or something like this has requirements that you depend on, so too can Helm have requirements that you depend on that are other Helm charts and things. So it provides a nice abstraction that makes creating things on Kubernetes very easily, and also exposes a lot of parameters where, you know, unlike apt-get or something where you just install it and there's no real parameters to fiddle with, most of your distributed architectures have more parameters than you could possibly shake a stick at. So those are all exposed to the command line as well. And that, not only do you just install the default, you can tweak and tune every single little bit of this kind of Helm chart. And so we've hosted it on our own local repo for now, but we're working to contribute this back to the stable Helm chart so that everyone can get like a nice 2.4 Spark cluster in a single line kind of thing. And so some of the basic architecture of this Helm chart that we've set up is we have a Spark cluster, of course, and it's running Spark Standalone for now because the Spark Kubernetes integration hasn't been fully GA yet. So we're kind of waiting on that to transition to the community adopted Spark Kubernetes, but it doesn't really matter too much. What really matters is kind of the infrastructure around this Spark cluster. And so some of the things that we've added a load balancer on top. So this is a component that normally isn't in a Spark cluster, but really should be if you want to use it as a web service hoster. So you have a load balancer that sits on top of the worker nodes to actually tie these different services that you create together into a single public endpoint. And that's fairly critical if you want to expose the services you make on Spark out to your users. And in addition, we have things like Jupyter and Zeppelin notebooks. So these are little servers that sit and can talk to the different Spark cluster and provide that nice notebooks API that you know and love if you're a data scientist. And also Livy, where Livy is the REST API on top of Spark Submit. So same words, but very different from what we're doing in that. These provide you a way to submit jobs, like full-on jobs, to Spark via REST. It doesn't let you submit data to Spark via REST. And so these are the different components that you might want in your Spark cluster, and they all come prepackaged in that Helm chart. And we're also working on adding cognitive service containers right alongside there. And so we'll talk a little bit more about that in the next talk at 3:30, I think, down in room 2009. And so I had mentioned that we can use a Helm chart in order to actually go about creating these services and tying them together with a load balancer. And another option that we're just kind of got working for this Spark Summit is a tight integration with Azure Machine Learning. So Azure Machine Learning is Microsoft's flagship machine learning project, and it aims to provide things like tracking your models, logging metrics for your models, and also it aims to provide a way to train your models on a variety of backends. The idea is that you should write code once and be able to throw it on a big cluster, or throw it on a single node, or throw it in a database, or something like this. And furthermore, one of the third pieces of functionality that's pretty critical is that it tries to provide a nice API for serving things on Azure, so that you write your Python code nice and simple, and it takes care of layering on an API and providing HTTPS and doing all of the stuff that you'd rather not do if you're a data scientist looking to crank something out super quick. And so the way that if you read the documentation in Azure Machine Learning before today, it basically says to use the batch API if you want to deploy a Spark job, that it will create a small single node Spark cluster on each one of your pods in Kubernetes or on each Docker container in Azure Container Instances. And you will handle the init and the run. And in the run, they say you should transform a batch data frame and return the results, and hence incurring the 500 millisecond latency. But what's nice is that in this init function, you can do arbitrary setup. You can set up all sorts of kind of things. And so what we've done is that we've added a sample where in the init function, you can set up Spark serving. So effectively, in these Docker containers, you have a running Spark server. And then you can just use request pass-through in the run to take your incoming requests from Azure Machine Learning, push them into Spark Serving, get them back, and send them out. And so this incurs a slight latency of maybe like half a millisecond or something, but it's certainly better than 500 milliseconds. And you can hook into all of the model management APIs. You can hook into all of that telemetry that you get with Azure Machine Learning. You just need to use a different scoring script. And so I mentioned that this is part of a larger project, and this project is called Microsoft Machine Learning for Apache Spark. It is kind of a home for Microsoft's open source contributions to Apache Spark. And today I touched upon Spark serving, but we have a lot of other different components in the Spark ecosystem. We have Lime on Spark for distributed model interpretability. We have idiomatic bindings for all of the cognitive services on Spark, so you can throw them into your existing SparkML pipelines. Provide a full integration with LightGBM. So if you've used this gradient boosting tree framework, you can now stick it into your SparkML pipelines and not have to worry about MPI and NITs and all this crazy stuff that you don't really want to think about when you're doing distributed computing. You just want to use that slick SparkML API. Got deep networks with CNTK that have roughly the same API as Spark's deep learning pipelines so that you can easily switch between CNTK and TensorFlow. And I mentioned HTTP on Spark today. So yeah, in conclusion, Spark Serving is an idiomatic way to deploy any Spark streaming computation as a web service. We get millisecond latencies. We have support for retries and continuous processing. You can get started now with interactive examples on our website. We have a few of them. And I would encourage you to check out our next talk at 3:30 in room 2009, which will really dive deep into the Azure cognitive services on Spark and how we can go beyond just calling cloud APIs and bring the services down into the clusters themselves to kind of enrich your clusters with Microsoft's proprietary cloud intelligence stack. And so, yeah, I encourage you to check it out. If you're interested in contributing, please let me know. If you find any issues or bugs, let us know on GitHub or through the website. And thank you very much to everyone who contributed to this already. And thank you all for listening. Yeah.
If you have any questions, there's a microphone in the center of the room. Please come to it for the recording.
I was wondering what the semantics of the trigger method were in the Spark serving.
Ah, yes. Great question. So let's find it. Yeah, so this trigger actually isn't Spark serving. This is Spark's continuous processing. And the idea behind trigger continuous 20 seconds is that in Spark's continuous mode, you still want to have fault tolerance, but you don't want to have micro batches per se. You want to just push things through the pipeline as they arrive. And so this continuous 20 seconds is, they use the special kind of checkpointing method so that every 20-second intervals is kind of like a micro batch, but it doesn't incur the overhead of a micro batch. And so I think that documentation will probably steer you right as to the exact semantics of what that continuous processing means. I know they use a very slick mathy checkpointing method that I like the idea of. And there's also other triggers, so you can set the trigger to be like a batch as soon as possible, or a batch every day, or a batch every week, or something like this. And in the web serving context, that's a little unnatural to just have a batch every day. It'd be like you open the gates and let people start talking to you, and then you close the gates very quickly. And so those are kind of more up in the air, but they exist, and so you could use them if you like.
Hey, this looks really cool.
Thank you.
Is there a can you send a bulk request that gets parsed into a data frame in multiple rows? Like if you want to do bulk scoring of several.
Sorry, can you repeat that? Can I send a what request?
Like a bulk request that that gets parsed into several distinct rows, like a JSON list or something.
Yeah, that's a great question. It's like, how do you handle a batch API in this particular kind of thing? And so the way that we've thought about this is that we've kind of left it up to the user. We've done the entire HTTP protocol, and you can really do whatever crazy stuff you want. And so the way that I would implement that is I would JSON have my schema that I'm parsing be a list of whatever you'd like, and then use the explode function in Spark, and that will take that list and split it up into multiple rows, and then you can treat it like batch. as long as you merge them back together. And in MML Spark, we've actually had to do this pattern a lot, this kind of like batching and rebatching. And so we have a local squash function that will take just the things with the right IDs and squash them together without actually doing a full shuffle. So that can help you out if you want to reply in bulk.
And then you could return whatever you liked, right? So if you wanted to return a separate, like keep hold of the IDs of the things and return a separate score per ID, that's all fine.
Yeah, so you can like play with those IDs all you want. We expose them in the data frame. And so if you want to do like crazy things where you could potentially like move them around and stuff like that, that's okay, I guess. Just don't break it.
Hi. Would you recommend this architecture on a mission-critical operation? That's the general question. I'll give you a little more detail. So, for example, we're taking in information from a potential customer, and we want to reply to them in some way immediately. Then we also want to record that historically this is a customer that has applied. Would you use this one ingest for those two purposes?
So you definitely can, theoretically, in that you have that ability to reply within the pipeline and then like keep that data flowing and write it out to a different sink. Maybe you want to write that out to Parquet or something like this. So we have that kind of ability within this system. In terms of the mission criticality of it, we're trying to make it as robust as possible. And so if any of you guys like find any issues, we'll be happy to patch them as immediately as possible and give you a new build. We can do that very rapidly. And so, yeah, I think that really what we're just trying to look for is to get the community to use this and then expand it and find whatever kinds of potential faults might be in there and purge them out so that we can then, go and commit this to core Spark or something like that.
Hi, is the load balancer that you showed and also the local server wrapping Spark Job Server at all, or using it?
Say again? This load balancer and the local server, what was that?
Are any of those using the open source Spark Job Server?
Yeah, that load balancer is something that you kind of have to bring to the party. I would love to know if there's already a load balancer somewhere in the existing Spark architecture that we can hook into so that we don't need to bring your own load balancer kind of thing. But from what we've seen, at least from our initial investigations, that's something that you kind of bring on top of your Spark cluster and stick on there. And this way you can configure it and manage it how you like.
Okay,
but yeah, we're really open to seeing like where in the Spark existing architecture we can reuse components. So I mentioned that shuffle service. If we can find a great way to hook into that, and we haven't found a great way to hook into that because it's not very well documented, but that's something we really would love to investigate.
Okay, thanks.
Hey, thank you. This is awesome. Can you do like zero downtime deployment of new models with this, if you have a new version?
So this might be a good feature to add. I think that there's a few potential ways you might consider it. You might want to have a new streaming pipeline and kind of do the zero downtime rotation up on a layer above. But this is something that potentially, if it's of great community interest, we can see if there's a really nice idiomatic way to do that from within the system as opposed to above the system.
So this is such in many ways, a mind-blowing sort of use of
nice.
Spark. I hope throughout the project you had lots of moments like, oh, what am I doing here? I'm not quite clear, when you say microbatching, does that mean that I'd have a data frame that potentially has multiple requests in it? Multiple requests in it, and then that would just be handled in batch, and then you send those out when you're
Yeah,
done?
so the idea is like in Spark streaming, you can kind of think of a streaming data frame as a data frame with like infinitely or arbitrarily many rows that come in as new data is coming in. And that's the way we kind of think about it here as well, in that a single data frame will hold all of the requests for all of your users, and then your logic maps those requests and does things with it in the same way that in Spark, you map and work with your rows. And so that is the idea. And that within a single partition, you will have multiple users. You can have some users, you can have no users if no one talks to that particular partition. So.
All right, everyone, let's give Mark a big hand.
Thank you, guys.